If you've dealt with linear algebra or any matrices, then you know something about the determinant. The determinant of a matrix is such a powerful tool that helps us understand whether or not a system of equations is going to have a solution. For example, if the determinant of a matrix is equal to 0, then it has no inverse, meaning it has no solution. And of course, if it's not equal to 0, then it's invertible. It's incredibly useful in something called Cramer's rule, and when you're studying calculus, specifically change of variables, then you know this as a Jacobian. And I think it's really important to understand the geometric relationship of the determinant. So let's visualize this. Let's just say we have two vectors on the xy plane. You have vector 1 with the components AC and vector 2 the components BD. We can go ahead and construct a 2 by 2 matrix, and then we're going to visualize what the determinant of A represents. And in school, you're taught that the determinant is the product of this diagonal minus the product of the other diagonal. But let's visualize this from a geometric standpoint. If you know anything about vector addition, you know that we can go ahead and replicate the V2 into the end of vector 1. And now we can do the same for V1 and put it on the end of vector 2. And what we have here is a specific area. But check out what happens. Up here is vector 2, so we can use the idea for vector 2 to find the B value there on the x-axis, and the top is going to represent C plus D. And now we can sort of break this down and create a rectangle with all these little pieces. Looking at this triangle right here, we have the base, which is A, we have the height, which is C, so we know that the area of this is AC over 2. This little rectangle right here is going to be B times C because the B and our C. Up here in the top left, we also have a B and C where we get the B value from the component of vector 2 and we get the C value from the component of vector 1. And up on top, we have another triangle, AC over 2. And now we have these two missing triangles, and that's going to be BD over 2. So if we wanted to find the area of the parallelogram that's in the middle, then we're going to go ahead and multiply the base, which is A plus B, times the height, which is going to be C plus D. But don't forget that we have to subtract the area of the 4 triangles and the area of the 2 rectangles. Now we just do some foiling, and you're going to see that the ACs cancel out, the BDs cancel out, and we have a BC minus 2BC giving us AD minus BC. And what do you know? That is equal to the determinant, and that is exactly what the determinant represents. That's the area formed by this parallelogram.